Anybody get this? How many of you got to this one, tried y equals x? What happens? What do you get? What does it turn into? This algebraically is really just what? X cubed over x squared plus x to the fourth, right? What can you do with this? You factor out an x squared. So you'll get x squared on top factored out. On the bottom, factor out x squared. You get 1 plus x squared, right? Cancel those out. So what happens here? If x goes to 0, what happens here? You get 0, don't you? You get 0? Does that help you? No, that didn't help. So what next? What's your next path? X equals y squared? Where's that coming from? From magic? X is y squared. So think about this. If this was y squared, then this would be what? Y to the fourth? And if this x squared was y squared, then you're taking y squared and squaring it, which again is y to the fourth. And so you'll have y to the fourth on top over 2y to the fourths, and that'll reduce and become the fraction 1/2. So that you have to just kind of understand what's happening in here, and that'll work. It'll work that way. Do y'all get that? So this path, what was it? X is what? X is y squared. X is y squared. So let me replace that. This limit's going to be limit. Instead of x, I'm going to put what here? Y squared. Y approaches 0, 0. Replace my x with y squared, so y squared times y squared on top over y squared squared plus y to the fourth. Which is essentially y to the fourth over 2y to the fourth, which turns into 1/2, doesn't it? And that's all we need to say it doesn't exist. Now, what does that path look like? It's parabola sideways. So if I approach 0, 0 on that path, I get 1/2. But if I approach along the x-axis, it's approaching 0. If I approach along the y-axis, it's approaching 0. If I approach along the diagonal, it's approaching 0. So this ought to be a pretty interesting looking function, right? Does anyone have any questions over that? We're good? I'm going to show you the picture of this one because it's pretty cool. There it is. Look at that top ridge. Can you see that top ridge? Right in there? See that top ridge? You're walking along that top ridge, you're up at 1/2. That's that parabola. But if you come in the y-axis or the x-axis, you're down at 0, even along the diagonal. So let's see. There's along the y-axis, it's 0. Along the x-axis, oh, can you see through? You can see through it, can't you? That's through. Now remember, at 0, 0, you have this undefined thing happening. Oh, this is cool. Let me show you this. Part of why I wanted to go through this. You know how we checked just a second ago? We checked y was x, right? Y equals x was one path. There's another path that you can choose that's really kind of, you've heard the term like killing 2 birds with 1 stone. This is killing an infinite number of birds with 1 stone. What I could do is come in on the path y equals mx. So think about this. Y equals mx is going to be a line that goes through the origin, right? If m is 1, then it's this one, isn't it? If m is negative 1, it's this one. If m is 2, it's this one. If m is 3, it's this one, right? So what I'm going to do is instead of fixing my slope, I'm going to let it be arbitrary. And now I'm going to rewrite that limit again. Limit, I'm replacing y with mx, so it's x, mx. I hope you understand we already have the answer to this problem. Do you all get that? Okay, but this is another choice you could do that is pretty powerful when it comes to actually evaluating this. So check this out. I'm replacing my y with what? Mx. So it becomes x times mx squared over what? X squared plus mx to the fourth. And the question is, what is this? So I'm going to have to be correct, precise with my notation, I need to rewrite this limit again, right? That's a lot to write, and it's class time. So I'm just going to write, this is all L, okay? I do that when I'm doing the homework problems, too, because it's too much writing. So this here, on a test, please write it down, okay? It's not that bad. What is the top here? M squared x cubed. On the bottom, x squared plus m to the fourth, x to the fourth. Yeah? All right, let's keep going. That limit becomes, this limit becomes factor out an x squared on the top. You're left with m squared x. And on the bottom, you're left with, let's see, pull the x squared out. You're left with 1 plus m to the fourth x squared. We good? Just algebra here? Cancel. And so we're left with limit as m squared x of m squared x over 1 plus m to the fourth x squared. So what am I supposed to let go to what here? Let x go to 0, and what do you get? 0, regardless of m, right? Regardless of what you choose m to be. If you choose m to be any number, go ahead, give me a number, fix it, I don't care what it is, this limit's going to go to 0, isn't it? For all m. So that means every path, this is crazy, think about this. If you draw me this right here and you approach 0, 0, if you approach that on any straight line, the limit is 0. But if you approach along x equals y squared, it's 1/2. So you would think that this takes care of every path, right? But they're all straight line paths. It has to hold for all paths, period. That's a very, very profound thing. So what I had done here is I had built into my code a way of actually changing the paths. So I'm going to take the surface out of here. And, well, I'll bring it in. And now I'm just going to rotate. Notice that all these different paths, if I look at it from the top, maybe that'll make a little more sense. All these paths that I have approach 0, 0 on any of these lines. Do you all see that? And if I look at the surface, and I start coming in from any of those lines, no matter what, when you approach 0, 0, oh, sorry. I'm looking at my screen, there's nothing there. So all this shit's getting in the way. See, no matter how I approach it, from which line, this black part is the actual part that's on the surface. They all want to go to 0, 0, like to 0, no matter what. It's pretty cool.
So should we try y equals mx after we try 0, 0?
You could. Sometimes the algebra of having mx in there can be pretty nasty. But you know that if you get an answer, then it's, So it's really up to you. I usually do x is 0, y is 0, y is x, hoping for the best. And if that doesn't work, then I think of mx, but I also think of, can I see what I can do to make it become a nice thing, like the x was y squared. Any other questions or comments? I'm going to go back to that in a second. We're going to look at this one. Look, you could spend all day trying to figure out two paths that make this one different, this limit. You could all day long. You're never going to get it because this limit does exist. All right? Every path as you go to 0, 0, every single path goes to the same thing. Now the question is, how do we show it if you can't check every path? And what we're going to use is something we had in Cal 1 called the squeeze theorem. What we're going to do is we're going to take this function and we're going to try and squeeze that thing between two things and then show that those two things go to the same place, which forces this one to the same place. So I think what I'll do is I'll start by writing down an inequality, because that's what you always need for the squeeze theorem, an inequality. And how you pick this, well, watch me and then maybe it'll make sense why I chose this. Do you agree that that quantity is greater than or equal to 0? Yes? Do you all agree with that? And do you agree that that's also less than or equal to 1? That's a little bit more difficult to understand, maybe. If I cover up this, 2y squared, what's x squared over x squared? 1, and then there would be equality, wouldn't there? Now, if I put a number in here, I'm adding 2 times y squared. This number, the least it could ever be is 0, right? Other than that, it's going to be a positive number. Added to x squared, this denominator would get bigger, right? If the denominator gets bigger, the ratio gets smaller. So this rational expression must be less than or equal to 1, right? Okay, so does everyone see that this piece in here is everything up there except the sine squared y? Everyone see that? So what I'm going to do now is I'm going to multiply each of these by sine squared y. So what's 0 times sine squared y? 0 is less than or equal to this times sine squared y, which is the thing I'm interested in, isn't it? Isn't that what I'm interested in? But that has to be less than or equal to 1 times sine squared y. You still with me? Why didn't I have to worry about flipping inequalities? Because don't you have to worry sometimes, like if you multiply by a negative, it flips? Why am I not concerned about that? It's not negative, sine squared, right? So it's never, that's not a negative number, so I don't have to concern myself with that. So what we do now is once we have the thing we're interested in, which is this, once we have it squeezed between two things, we need to make sure that these two things go to the same value as we approach in a limit. So what I need to do is this now. I need to set up this inequality again with limits. So this right here, I want the limit as xy goes to 0, 0 of 0, that's this one, is less than or equal to the limit as xy goes to 0, 0 of x squared sine squared y over x squared plus 2y squared. That's less than or equal to the limit as xy goes to 0, 0 of sine squared y. Yeah? Is it going to get squeezed? We don't know what this is, right? This is what the whole problem started as, right? This limit, whatever it is, must be greater than that limit right there. What's this limit right here? The limit of a constant is going to 0. That must be less than or equal to this, right? Which we don't know. We're trying to figure out what the hell that is. But that must be, what? Less than or equal to whatever that limit is. And do you see what's good about this limit? X isn't even here, right, which is nice. And if y goes to 0, sine of 0 is 0. 0 squared is 0. So this limit is just 0. So what's the only possibility? If we're saying this limit has to be somewhere between 0 and 0, it must be 0. That's the squeeze theorem. You've squeezed it. Now, you can mess the squeeze theorem up. Because if, let's say you try and do some nice stuff, and then you get something over here, like let's just say for the hell of it, that this was this, right? Let's just say. Then you would be squeezing it between where and where? 0 and 1. Well, congratulations. You have a window of where it is, But that means that it could be fluctuating. It could be 1/2, then it could be 3/4, and then back to 1/2 and 3. So it's in a window. That does not nail it down. It has to be going to the same place on both sides, which is what we had. So we're happy about that. But I had to be clever, kind of clever, about the way I set up my initial inequality, right? And that's what the most challenging thing is for these types of problems. On a test, if I were to give you a problem like this, I will tell you, show the limit exists. And if I say show the limit exists, then you know automatically it's going to be something like this. If I say something like show the limit does not exist, then you're going to be testing paths. See the difference in the language? Okay. There's also a problem on the homework where it says to show the limit exists. And what they do, it's crazy. You'll see it when you get to it if you work on it, is that they don't even do a squeeze theorem. They just look at the original limit that looks like something like that. There's the original limit. And it has some radicals in it. And they just come in and multiply the top and bottom by the conjugate. Remember the conjugate? And when they do that, it becomes a new thing, and it's a real easy limit. But again, it's not a very natural move just to come in with the conjugate. But it works. So be prepared for that. You'll see it on the homework. I think that's it. Continuity, not really going to get too much into this. Continuity back in Cal 1 just meant that you have a function. There you would say the limit exists, right? For continuity, we would actually need the function to be defined there, and it would fill in that hole, right? Same sort of thing for these surfaces. If we want a function of two variables to be continuous at a point, then the limit actually has to exist. So from every path, it's going to the same value. And when you actually get to that value, it's filled in. So there's no puncture in the surface, right? But we're not going to show continuity or anything like that. But we will use this result. And this, again, ties into Cal 1. What types of functions are continuous? So from Cal 1, all polynomials are continuous. All trig functions and rational functions are continuous on their implied domains. So it's kind of the same sort of thing. All polynomial functions of x and y are continuous everywhere. All rational functions are continuous on their implied domains. And the composition of continuous functions are continuous on their implied domains. So I guess all that's saying right here is that